The stars could be within our reach within a single lifetime. This is the bold promise of the Alcubierre warp drive, a concept that does not break the universe's speed limit, but cleverly bends the rules. By the end of this exploration, you will understand the real physics that could one day make interstellar travel a practical reality. We will uncover how a warp bubble might compress the fabric of space itself and confront the terrifying hazards that could lurk within it. What does it truly mean for humanity to finally leave its cradle? Think of that speed limit not as a suggestion, but as the very geometry of reality. Einstein revealed that space and time are not a static stage but a dynamic fabric, and the speed of light is the ultimate throughput of that system. It is the maximum rate at which any information, any influence, any particle can travel through the cosmos. For a spacecraft, this creates a profound and frustrating paradox. To go faster, you add energy, but as you approach light speed, relativity dictates that your mass effectively increases, requiring even more energy to accelerate further. It is a feedback loop that spirals toward infinity. To reach the exact speed of light, a ship with any mass at all would need an infinite amount of fuel, an impossibility that firmly slams the door on faster than light travel through conventional propulsion. This transforms the distances between stars from mere measurements into walls of time. A journey to our closest stellar neighbor, Proxima Centauri, at a significant fraction of light speed would still take years. For more distant stars, the voyage stretches into centuries or millennia, demanding ships that are less like vessels and more like self-contained, flying civilizations. This is the great silence we perceive when we look up, not an empty sky, but one separated by a chasm of time we cannot cross. So if we cannot move faster through space, what other variable in the equation can we change? The answer lay not in speed, but in the very shape of the journey itself. In 1994, a Mexican theoretical physicist named Miguel Alcubierre was wrestling with Einstein's own rules, searching for a loophole written in the language of geometry. His question was deceptively simple. If a ship cannot travel faster than light through space, could space itself be persuaded to move instead? The equations of general relativity describe how mass and energy warp the fabric of spacetime, creating what we feel as gravity. Alcubierre asked if we could design a specific, deliberate warp, a controlled distortion with a very special purpose. What he found was a mathematical possibility so elegant it felt like a magic trick. He proposed creating a bubble of flat, normal spacetime around a spacecraft. Then he would manipulate the geometry outside that bubble. The spacetime directly in front of the ship would be compressed, pulling the destination closer. The spacetime directly behind the ship would be expanded, pushing the point of origin farther away. Inside its quiet pocket of reality, the ship would be motionless. It would not be flying to the star would be pulled toward it, while the space behind it rushed outward like a wake. The ship surfs a wave of spacetime itself, never locally exceeding light speed, yet covering interstellar distances in a fraction of the time. When Alcubierre published this model, it sent a shockwave through the physics community. It was a rigorous proof that a warp drive, in principle, was not forbidden by Einstein's theory. The paper was a revelation, a permission slip to dream on a cosmic scale. But like all permissions, it came with a daunting and expensive list of requirements. The blueprint was drawn, but it called for materials and energies that seemed utterly impossible. Alcubierre's blueprint gave us a radical new shape for a journey, but to build it we must understand its geometry. Think of the warp bubble not as a simple sphere, but as a self-contained pocket of normal reality. Inside this pocket, the spacecraft rests in perfectly flat spacetime. The astronauts would feel no acceleration, no crushing G-forces, because their local environment is utterly still. They could float a cup of coffee in the air and it would hang there undisturbed, even as their bubble traverses light years. This is the first miracle of the design, the complete absence of inertial forces that would pulverize a conventional ship at such phenomenal speeds. The magic and the immense challenge lies in the walls of this pocket. These are not solid barriers, but boundaries of extreme spacetime curvature. Picture the bubble moving from left to right. The spacetime directly in front of the ship, just outside the forward wall, is under tremendous compression. It is as if you are taking the vast, empty distance to a star and crumpling it like a piece of paper, bringing the destination dramatically closer. This region functions like an artificial gravitational well, pulling the bubble forward. Simultaneously, the spacetime directly behind the ship undergoes our opposite, equally profound transformation: rapid expansion. The space you just traveled through is stretched and inflated, pushing your starting point far into the cosmic distance. This expansion creates a kind of negative pressure or push from behind, so the bubble is pulled forward by compressed space and pushed from behind by expanding space. The ship itself is just along for the ride, a stationary passenger on a moving walkway made of the cosmos' own fabric. This elegant arrangement solves one of relativity's great puzzles for travelers: time dilation. At near light speeds, time inside a speeding ship slows down relative to the universe outside. A crew might reach a star in what felt like months, only to find centuries had passed at home. But inside the warp bubble's flat spacetime, since the ship isn't moving through space locally, this extreme time dilation does not occur. The clocks of the crew and mission control could, in theory, tick in sync. You would not lose the world you left behind, yet those bubble walls where spacetime is so violently bent hide the true cost of this miracle. Creating such curvature requires something extraordinary, a form of matter with negative energy density, or what physicists call exotic matter. This is not just a rare or powerful fuel, but a substance that bends the fabric of reality in the opposite way that normal mass does. It would generate a kind of anti-gravity, repelling spacetime rather than attracting it. Without it, the bubble cannot form. So while the anatomy of the warp drive is beautifully clear in theory, its construction hinges on a material that may not exist in our universe, or that lies far beyond our current ability to create or contain. The design is complete, but the foundation is made of ghostly, hypothetical stuff. This brings us to the central, towering obstacle, the one that transforms a brilliant blueprint into a ghostly mirage. The Alcubierre drive requires a fuel that defies our everyday experience of reality. It does not need more power or a cleaner energy source. It needs a substance with a property so strange it sounds like science fiction: negative energy density. To understand why this is so crucial and so difficult, we must first look at what normal matter does. Everything you see around you, from the screen you are watching to the planet beneath your feet, is made of atoms with positive energy density. This positive density warps the fabric of spacetime inward, creating the attractive force we know as gravity. It is why apples fall from trees and planets orbit stars. The warp drive, however, needs to do the exact opposite. To inflate the space behind the bubble and compress the space in front, it requires a repulsive force, a kind of anti-gravity. This is the role of exotic matter. In theory, this substance would possess negative energy density, meaning it would bend spacetime outward, creating a hill instead of a valley. It would push space apart rather than pulling it together. Without this repulsive effect, the delicate geometry of the warp bubble simply collapses. It is the essential scaffolding that holds the entire structure together. For a moment, this might seem utterly impossible, a violation of how the universe works. Yet, remarkably, our deepest theories of physics do not completely rule it out. At the quantum scale, the realm of the unimaginably small, the vacuum of space is not truly empty. It seethes with virtual particles flickering in and out of existence. This quantum foam creates tiny fluctuations in energy. Under certain conditions, like between two incredibly close parallel metal plates in what is called the Casimir effect, researchers can measure a region with a net negative energy density. The space between the plates has slightly less energy than the surrounding vacuum. This is a monumental discovery in principle, proving that negative energy density is not just a fantasy, it is a real, measurable quantum phenomenon. But here lies the staggering gap between a laboratory curiosity and a starship engine. The Casimir effect produces a negative energy density so minuscule it is almost beyond comprehension. To stabilize a warp bubble large enough for a spacecraft, calculations suggest you would need to concentrate negative energy on a cosmic scale. Early estimates were apocalyptic, requiring the negative mass energy equivalent of an entire galaxy. More refined models have brought that number down, but it remains daunting. Some calculations point to needing the mass energy of a giant planet like Jupiter, converted entirely into this exotic form. We are not talking about mining an asteroid for fuel. We are talking about harnessing or creating a form of matter that, for all practical purposes, does not exist in any usable amount in our universe. This transforms the challenge from one of engineering into a fundamental quest. It forces us to ask not how we build the engine, but whether the universe even allows for the ingredients in the quantities we need. The search for a path around this enigma is where theoretical physics becomes a frontier of cosmic possibility. The sheer scale of the original requirement felt like a cosmic veto, a universe politely informing us the idea was simply too grand. Those early calculations were not just daunting, they were absurd, suggesting you would need to convert the mass energy of something like Jupiter or even larger celestial bodies into exotic matter. It was a number so vast it effectively ended the conversation before it could begin, relegating the warp drive to the realm of pure mathematical fantasy. But science has a beautiful habit of revisiting its own assumptions. A pivotal turn came from researchers like Dr. Harold Sonny White and his team at NASA Eagleworks Laboratory. They asked a subtle but revolutionary question: what if the shape of the bubble itself was the problem? Alcubierre's original model envisioned a perfectly flat region inside an impossibly thin, sharp shell of warped spacetime. Dr. White and others explored a different geometry, a thicker, oscillating ring of warped space, more like a donut or torus surrounding the ship. This seemingly minor tweak in the mathematical model had a staggering consequence. The titanic energy requirement, once equivalent to a planet, collapsed by many orders of magnitude. In some of their refined models, the negative energy needed dropped to something comparable to the mass of the Voyager 1 probe. Now, do not misunderstand. We are not saying you could power a warp drive with a few kilograms of exotic matter. The challenge remains monumental, as creating and stabilizing any amount of this hypothetical substance is far beyond us. But the conceptual shift is everything. The energy barrier was transformed from an eternal, fundamental no into a temporary, engineering not yet. This recalculation did more than adjust a number on a page. It changed the entire emotional and intellectual landscape of the field. It moved warp drive theory from the fringe of impossibility to the frontier of theoretical plausibility. Researchers could now focus not on whether it could ever be possible, but on what specific, unknown physics might one day make it so. The question became a catalyst, pointing toward the deepest mysteries we have yet to solve, like the nature of quantum gravity and the true behavior of spacetime at its most fundamental level. The dream was no longer forbidden, merely deferred, waiting on a future breakthrough in our understanding of the cosmos itself. The universe keeps its most profound secrets in the smallest of places. While we speak of the cosmic scale of warp drives, the key to their impossible fuel might be hiding in the ghostly whispers of empty space itself. This is where the Casimir effect offers a tantalizing glimpse into a reality far stranger than fiction. Picture not a laboratory of complex machinery, but a deceptively simple setup: two perfectly smooth, uncharged metal plates, placed so close together they are separated by a gap thinner than a wavelength of light, suspended in a perfect vacuum. In our classical, everyday view of physics, nothing should happen. There is no electric charge, no magnetic field, no obvious force at play. Yet, when scientists perform this experiment, they measure a faint but undeniable pull. The plates are drawn together by an invisible hand. This force is the signature of the quantum vacuum, the seething, energetic froth that underlies what we perceive as nothingness. According to quantum theory, empty space is not empty at all. It is a turbulent sea of virtual particles, pairs of matter and antimatter that spontaneously blink into and out of existence, borrowing energy from the vacuum for the briefest moments allowed by uncertainty. These fleeting fluctuations exert a subtle pressure everywhere. Now, place those two plates incredibly close together. The gap between them is so narrow that only certain wavelengths of these virtual particles can fit inside. The wider space outside the plates, however, allows for all possible wavelengths. This creates an imbalance. The pressure from the particle fluctuations outside the plates becomes slightly greater than the pressure from the restricted fluctuations between them. The result is a net push inward, forcing the plates together. Crucially, this means the region of space between the plates has a slightly lower energy density than the natural vacuum. In the precise language of physics, it exhibits negative energy density. That phrase is the bridge between a quantum curiosity and a star-spanning dream. The Casimir effect is a real, measurable, repeatable laboratory demonstration that negative energy is not a mathematical fantasy. It is a genuine feature of our universe, mandated by the laws of quantum mechanics. For a moment, it feels like a revelation. The exotic matter we need is not just theoretical. It is literally all around us, woven into the fabric of the void. But the scale of the challenge immediately reasserts itself. The negative energy produced in a Casimir experiment is almost unimaginably tiny. To power a warp bubble, we would need to somehow harvest, concentrate, and stabilize this quantum effect on a scale billions upon billions of times greater. It is the difference between feeling the gentle tug of a single thread and needing to lift an entire mountain with that same thread. So while the Casimir effect does not provide a solution, it provides something perhaps more valuable, a principle. It tells us the universe's ledger does, in fact, allow for negative entries. The fuel for a warp drive is not forbidden by the laws of physics as we understand them. The problem is one of magnitude and engineering, not of fundamental impossibility. This shifts the quest from searching for a mythical substance to confronting a monumental question of amplification. How do we take a whisper from the quantum realm and turn it into a shout that can bend the cosmos? That question leads us from the quiet of the laboratory to the raw, untamed frontiers of physics, where the answers may lie in energies and densities that defy our current imagination. Yet, even if we somehow master the physics of negative energy, a far more subtle trap awaits within the bubble itself. The mathematics reveals a chilling limitation, not of power, but of perception and control. It is called the horizon problem, and it transforms the warp drive from a ship into a potential prison. Remember the anatomy of the bubble. The crew resides in a pocket of perfectly flat, normal spacetime, a safe little room. But the walls of that room, where spacetime is violently compressed in front and expanded behind, are not just boundaries, they are horizons in the relativistic sense. Any signal, a radio wave, a laser pulse, a simple shout travels at the speed of light. But the warp bubble's walls are moving faster than light relative to the outside universe. A signal sent from the ship toward the front wall to, say, initiate deceleration or change course can never catch up to it. It is like trying to throw a paper airplane forward from the back of a supersonic jet. The airplane is immediately swept backward, unable to reach the cockpit. From the crew's perspective, they are causally disconnected from the very machinery that propels them. They are passengers in a sealed train car, hurtling down a track with no access to the engine or the brakes. They could not steer around a cosmic hazard or even choose when to stop. The journey would have to be pre-programmed with absolute precision before departure, a single, irreversible leap into the unknown with no capacity for mid-course correction. This is not a minor engineering hiccup. It strikes at the very purpose of exploration, which requires the ability to observe, react, and decide. Some theorists have proposed potential workarounds that sound like science fiction because they are. One idea involves exploiting quantum entanglement or other forms of quantum non-locality, where particles can influence each other instantaneously across vast distances, seemingly bypassing the speed of light limit. If the bubble's control mechanisms were somehow entangled with systems inside the ship, a command could, in theory, affect the walls without a signal having to travel through the forbidden space. But this is purely speculative, pushing against the very edge of our understanding of quantum mechanics and how it might or might not integrate with gravity. The horizon problem forces a profound realization. A functional warp drive is not merely an engine you build and fuel. It is an environment you must be able to interact with. The challenge shifts from bending spacetime to communicating with it, from creating a wave to learning how to surf it with intention. Without solving this, the greatest voyage humanity could ever undertake becomes a glorified, unstoppable cannonball shot into the dark. But the horizon problem is not the only silent killer waiting in the warp. The very act of bending spacetime at such speeds may awaken a far more violent and fundamental danger, one predicted by one of the greatest minds of our time. Stephen Hawking, in his work on black holes, uncovered a profound link between gravity, quantum mechanics, and thermodynamics. His famous prediction of Hawking radiation suggested that even the darkest, most forbidding objects in the universe are not completely black. At the very edge of a black hole, its event horizon, the immense gravitational field can wrench virtual particle pairs from the quantum vacuum. Normally, these pairs annihilate each other in an instant. But if one particle falls into the black hole, its partner can escape as real radiation, slowly causing the black hole to evaporate. This radiation is incredibly faint for a stellar black hole, but it represents a fundamental principle. Intensely warped spacetime interacts violently with the quantum foam of empty space. Now apply this principle to the Alcubierre bubble. Its walls are not event horizons, but they are regions of extreme spacetime curvature, moving faster than light. Some theoretical models suggest a similar, terrifying process could occur here. As the bubble plows through the universe, it would not travel through a pure, empty void, but through that seething quantum vacuum. Virtual particles constantly popping into existence near the bubble's boundary could become trapped by the intense warping. One member of a pair might be caught on the outside of the bubble wall, while the other is swept inside. They cannot annihilate. The particle inside the bubble would become real, carrying energy. But this energy does not come from nowhere. It would be extracted from the warp field itself or manifest as radiation. Critically, this radiation would not dissipate. Because the bubble moves faster than light, the radiation generated at the front wall cannot stream away into space ahead of it. There is no ahead for it to go. Instead, theoretical work suggests it would accumulate, piling up just in front of the bubble like a bow wave of pure energy. Imagine driving a car through a blizzard with the windshield wipers turned off. The snow does not blow past you. It simply builds and builds on the glass until you can no longer see. In the warp bubble's case, the snow is not harmless flakes, but a concentrated flux of high-energy particles and radiation. For a short hop, this might be negligible. But for an interstellar journey spanning light years, the buildup could become astronomical. The moment the ship decelerates and the warp field collapses, that entire accumulated energy front would be released. It would flood into the bubble's interior in an instant. The result would not be a gentle glow, but a cataclysm, a wall of radiation so intense it would sterilize the ship, reducing it and its crew to their most fundamental particles. This is not a problem of shielding or hull design. It is a problem of geometry and fundamental physics. The warp drive, in this view, might be less like a starship and more like a cosmic lightning rod, gathering a lethal charge over its journey that it can only discharge upon arrival, with itself as the target. This potential hazard transforms the challenge from one of mere construction to one of cosmic negotiation. It suggests the universe may have a built-in cost for cheating its speed limit, a toll paid not in exotic matter, but in raw, destructive energy. To solve it, we would need a deep and complete theory of quantum gravity, a way to understand how space-time curvature and quantum fields dance together not just at the edge of a black hole, but at the boundary of a machine of our own making. The silence of the stars may not be emptiness but a warning. The universe is not an empty highway. It is a complex, dynamic landscape filled with obstacles we cannot see. Navigating it with a warp drive would be less like piloting a ship and more like threading a needle through a storm of invisible needles, all while blindfolded. The fundamental problem is this: the warp bubble does not move through space, it moves space itself. Anything caught in its path is not simply impacted, but becomes part of the violent geometry of the warp field. Consider a single microscopic grain of interstellar dust, a common sight in the void between stars. To a conventional ship at sublight speeds, it might be a minor hazard, a tiny pit on the hull. But to a warp bubble, this speck is swept into the region of spacetime, being catastrophically compressed at the leading edge. The dust particle would be blue-shifted, its energy amplified to an extreme degree as space is crunched around it. Calculations suggest even these tiny particles could be transformed into bursts of high-energy radiation, like cosmic rays, potentially flooding the interior of the bubble. A journey through a typical interstellar cloud could subject the ship to a continuous, deadly barrage, turning the serene pocket inside the bubble into the heart of a radiation storm. The ship's hull offers no protection because the radiation is generated within the warped space of the bubble itself. This transforms space from a medium to travel through into a minefield to be meticulously mapped and avoided, requiring sensors of unimaginable sensitivity to chart a perfectly clear path light years in advance. The perils only multiply upon arrival. Stopping is not a matter of firing retro thrusters. It requires the carefully controlled collapse of the warp field itself. If this is done incorrectly, the energy contained within the warped spacetime, including all that accumulated radiation from the journey, would be released in a sudden, catastrophic burst. An uncontrolled deceleration could inadvertently deposit the equivalent of a supernova's worth of energy into the very star system you hope to visit. The goal of exploration would become an act of unintentional destruction, sterilizing any potentially life-bearing worlds in a flash of gamma rays and high-energy particles. This forces a profound ethical dimension onto the technology. A warp drive is not merely a means of travel, it is a weapon of astronomical power, and its safe use demands a level of foresight and control that borders on prescience. You would need to know not just where you are going, but the exact composition of every cubic light year along your route, and calculate the precise millisecond to disengage the field to deposit your ship safely into normal space without unleashing havoc. It demands a navigation system that integrates real-time cosmic cartography with predictive models of quantum vacuum fluctuations, a computer and sensor suite far beyond anything we can conceive. The challenge shifts from bending spacetime to understanding it with an intimacy and precision we currently lack, seeing the universe not as a collection of stars, but as a delicate, energetic tapestry we must learn to touch without tearing. This entanglement of space and time reveals an even deeper, more unsettling consequence. If a warp drive can manipulate the fabric of spacetime to outpace light, it may inadvertently unlock a door we were never meant to open, a door to the past. The equations of general relativity are strangely permissive on this point. They suggest that with the right configuration of warp fields, you could create a path through the cosmos that does not just connect 2 points in space, but 2 moments in time. Physicists call this a closed time-like curve. Imagine drawing a line on a map that represents your journey. Normally, that line goes forward from departure to destination. A closed time-like curve is a line that loops back, connecting the destination to the point of departure in time as well as space. In theory, a ship following such a curve could arrive back at its starting point before it ever left. This is not science fiction speculation, but a sober mathematical possibility that emerges from the same physics that allows for the warp bubble itself. The most famous illustration of the problem this creates is the grandfather paradox. Suppose you used such a timeline looping journey to travel to a time before your grandfather met your grandmother. If you were to intervene in a way that prevented that meeting, you would logically prevent your own birth. But if you were never born, you could never have traveled back in time to intervene in the first place. The event contradicts its own cause, creating a logical knot that reality seems incapable of untying. This paradox is not about the mechanics of time travel, but about the fundamental consistency of the universe. It suggests that if backward time travel were possible, the chain of cause and effect that gives our reality structure and meaning could simply unravel. Some researchers, like Stephen Hawking, proposed a chronology protection conjecture, a hopeful idea that some yet unknown law of physics, perhaps from the quantum realm, would always act to prevent these loops from forming, like a cosmic immune system defending causality itself. But we do not know if such a law exists. The mere possibility forces a profound philosophical shift. It means that the ultimate technology for mastering space cannot be considered in isolation. It is inextricably linked to the flow of time. Building a warp drive would not just be an engineering challenge, it would be an experiment with the foundational logic of the universe. We would be moving from passengers in time to potential editors of it, with consequences we cannot possibly foresee. The silence between the stars might not just be a barrier of distance, but a safeguard for the timeline itself. The equations on the chalkboard are only the beginning. For a dream to become real, it must leave the page and enter the world of measurement, of tools, of tangible, if minuscule, effects. This is the monumental leap attempted by a small, pioneering team at NASA, known as Eagleworks Laboratories, led by physicist Dr. Harold White. Their mission was audacious: to take the Alcubierre warp drive, a concept existing only in the language of tensors and spacetime metrics, and search for its faintest whisper in a laboratory. This was not about building a Starship engine. It was about answering a more fundamental question. Can we even create, at any scale, the kind of spacetime geometry the theory requires? Their tool for this search was as elegant as it was ambitious, an instrument called the White-Jude warp field interferometer. Think of it not as a massive machine, but as a device of exquisite sensitivity, designed to detect distortions in spacetime itself. At its heart was a simple principle: a laser beam split into 2 paths. One path would travel through a region of space they hoped to subtly manipulate, while the other traveled a reference path. If the experimental apparatus could create even a microscopic warp effect, it would alter the path length of that laser beam by a minuscule amount, causing the two beams to recombine with a shifted interference pattern. Detecting that shift would be like measuring the ripple from a single pebble dropped into a cosmic ocean. To try and create that ripple, they employed a high-voltage device, essentially aiming to use intense electrical fields to stress the fabric of spacetime in a specific way, guided by their refined mathematical models. The results to date have not yielded conclusive evidence of a warp field. No definitive, repeatable signal has emerged from the noise, but to judge this work by that single metric is to miss its profound significance entirely. Eagleworks represented a crucial philosophical revolution. For decades, warp drive theory was the domain of mathematicians and theoretical physicists, a fascinating but abstract exercise. Dr. White and his team changed the conversation. They asked, what if we stop just calculating and start testing? They moved the concept from the realm of pure theory into the domain of experimental physics. They built hardware to probe a hypothesis. This shift is everything. In science, an idea that cannot be tested remains a philosophy. By designing an experiment, however preliminary, they transformed the warp drive from a speculative what-if into a series of empirical questions. How do we generate the necessary spacetime curvature? How would we measure it? What does the quantum vacuum do in this configuration? Each null result, each experiment that showed no effect, was not a failure. It was data. It helped refine the models, tighten the requirements, and teach us what does not work. Their work stands as a powerful testament to a principle that drives all frontier science. If something is not explicitly forbidden by the laws of physics, then it resides within the domain of the possible. Our task is not to dismiss it, but to probe its boundaries, to search for the cracks in impossibility through which a future might one day shine. This relentless, incremental testing is the quiet, unglamorous work that turns science fiction into science fact, one careful measurement at a time. Science fiction gave the dream a name long before physics gave it an equation. The iconic hum of the Starship Enterprise engaging its warp drive is a sound that has echoed through generations, a promise that the stars were not just points of light but destinations. Star Trek's brilliant narrative invention was its warp factor system, a clean, scalable metric that handily bypassed the crushing realities of relativistic time dilation. It allowed Captain Kirk and his crew to visit a new alien civilization each week, making the galaxy feel not just reachable but intimate. This was not hard science, but it was powerful storytelling. It embedded in our collective consciousness a very specific vision of humanity's future, one where we are a traveling species, united in curiosity, navigating a cosmos filled with wonder and conversation. For millions, this was their first encounter with the idea that the speed of light might be an obstacle we could engineer our way around. It made the incredible feel routine, and in doing so, it planted a seed of expectation that real science is still striving to meet. The cultural footprint of this idea is immense. It has inspired countless young minds to pursue careers in physics, engineering, and astronomy, not because they wanted to study fiction, but because the fiction pointed them toward a real and tantalizing mystery. It provided a shared vocabulary terms like warp drive, subspace, and inertial dampeners. That gives us a shorthand for discussing profoundly complex concepts. When Miguel Alcubierre published his paper, many people understood its significance immediately, not because they grasped the tensor calculus, but because they had spent a lifetime watching a version of it on screen. Science fiction primes the public imagination, making the arrival of a serious scientific theory feel less like a cold abstraction and more like the next logical step in a story we have been telling ourselves for decades. This priming is crucial. It builds a bridge between the laboratory and the living room, generating the cultural support and fascination that can help sustain long-term, high-risk research. Yet, as our scientific understanding has deepened, so too has our fiction. Look at a modern series like The Expanse. Its vision is grittier, anchored in a sub-light solar system where travel between planets takes weeks or months. Communication suffers under light speed delays, and human bodies are brutally punished by high-G maneuvers. This is a universe built on known physics, and it feels palpably different. The tension, the politics, the very shape of human society is dictated by the unforgiving tyranny of distance and momentum. Within that realistic framework, the sudden, shocking introduction of a protomolecule-based technology that can ignore inertia and distance is utterly transformative. It is not just a new engine, it is an earthquake that shatters every political, economic, and military assumption in the system. This contrast is instructive. It shows us that a true warp drive would not simply be a faster rocket. It would be a fundamental rewrite of human circumstance, dissolving the barriers that have defined all of history. The long cultural journey from the optimistic warp factors of Star Trek to the hard physics of The Expanse and back to the rigorous equations of Alcubierre creates a fascinating dialogue. One side asks, what does this future feel like? The other asks, what would it truly take to get there? Together, they perform an essential alchemy. They transform a mathematical possibility from a mere thought experiment into a cultural artifact, a shared dream that feels increasingly like a destiny waiting to be claimed. This dream does more than inspire engineers. It shapes the very questions we ask of the universe, guiding our search for the loopholes in reality that might one day let us step through. While the warp drive remains a distant beacon on the horizon, humanity is not waiting idly for its light. We are already learning to sail on beams of light itself. The most audacious proof of this is the breakthrough Starshot initiative, a project that sounds like pure science fiction but is grounded in engineering we possess today. Its goal is staggeringly simple and staggeringly difficult: to send a fleet of tiny spacecraft, each no larger than a postage stamp and weighing barely a gram, to our nearest stellar neighbor, Alpha Centauri, within a single human generation. These would not be mighty vessels with roaring engines, but silent, wafer-thin chips attached to gossamer-thin light sails. The propulsion would come not from onboard fuel, but from an immense array of powerful, ground-based lasers focused on those sails. The concentrated energy of that light beam would push the nanocraft, accelerating them to an unprecedented 20% of the speed of light. At that velocity, the 4.4 light-year journey would take just about 20 years. Imagine that, a spacecraft built with technology not far from what is in your smartphone, embarking on a voyage that for millennia was the stuff of myth. This is not a distant dream, it is a project with a concrete roadmap, tackling problems we can actually solve. It forces us to answer questions we will need for any interstellar future. How do you build a spacecraft durable enough to survive a 20-year bombardment by cosmic rays and microscopic dust at relativistic speeds? How do you power its instruments, and most crucially, how do you get a whisper of data back across that immense void to Earth? Starshot's proposed solutions are marvels of miniaturization. Cameras, thrusters, and communications lasers all etched onto a single chip, powered by a radioactive isotope or a microscopic nuclear battery. The data would be sent home via a tiny laser, a signal so faint that receiving it would require a network of telescopes acting as one giant eye. Every one of these challenges, materials, propulsion, communication, is a frontier of its own. And this is where the true synergy lies. The relentless pursuit of a warp drive and the pragmatic engineering of Starshot are not competing paths. They are complementary strands of the same great endeavor. The materials developed to shield a nanocraft from interstellar dust are the first steps toward understanding how to protect a warp bubble from the same hazards. The mastery of precision, phased array lasers for propulsion, directly informs the kind of energy control we would need to create or stabilize a warp field. The struggle to communicate across light years teaches us the absolute limits of sending information through space, a lesson vital for any future where we might need to guide or control a vessel moving faster than those signals. Starshot represents a philosophy of incremental, relentless expansion. It is about reaching outward with the tools we have, while we simultaneously probe the fundamental physics that might give us entirely new tools. One path seeks to cross the ocean with the most advanced canoe we can build today. The other seeks to discover the principles of the steam engine. Both are essential. The canoe voyage teaches us about the currents, the weather, and the nature of the sea itself, knowledge that will be priceless when we finally launch the steamship. So as we gaze at the sublime mathematics of spacetime curvature, we must also celebrate the painstaking work of engineers perfecting a laser array or a gram-scale spectrometer. They are not just building a probe, they are building the foundation of an interstellar culture, one stubborn, brilliant breakthrough at a time. The power to reshape the cosmos would inevitably reshape us. Possessing a warp drive would place a choice of unimaginable consequence into human hands, a choice that extends far beyond engineering. Who, in such a future, would hold the keys to the stars? The staggering resources and intellect required to build the first drive suggest it would not emerge from a garage workshop, but from the coordinated might of nations or planet-spanning corporations. This concentration of power presents a fundamental dilemma. Would this technology be managed as a common heritage of humanity, a vessel for pure scientific discovery and cultural exchange, or would it become the ultimate strategic asset, a new frontier for geopolitical rivalry, economic exploitation, and the painful amplification of existing inequalities on Earth? The very structure of the vessel could dictate the structure of society. If only the wealthiest or most powerful could afford passage, the stars would not symbolize unity, but become the ultimate gated community, leaving the rest of humanity watching from the shores of a single world. The dream of exploration risks being overshadowed by the specter of a cosmic caste system. Arrival at a new world introduces another layer of profound responsibility. The principle of planetary protection, which guides our robotic missions today to avoid contaminating other worlds with Earth microbes, would become an imperative of interstellar law. A habitable exoplanet is not a blank slate waiting for our footprint. It is a unique biological and evolutionary record, potentially billions of years in the making. Our first duty would be one of humility, to observe and study without causing irreparable harm. But what if that world holds resources vital for the survival of our own civilization? Who has the right to extract them, and under what ethical framework? The concept of ownership, so rooted in terrestrial law, shatters against the scale of a galaxy. Would we repeat the patterns of our history, or could we forge new traditions of stewardship, recognizing that with the power to take comes the profound responsibility to preserve? Most staggering of all is the possibility of encountering life, not as microbes but as intelligence. A warp drive does not merely shorten distance, it collapses the isolation that has defined our entire existence. We would no longer be a lonely voice shouting into a silent void, but a visitor approaching the doorstep of another mind. This moment would complete the revolution begun by Copernicus, who moved us from the center of the universe. It would force us to see Earth not as a singular oasis, but as one garden among many in a vast living cosmos. How we approach that doorstep would define our species for eternity. Would we come as conquerors, as curious scholars, or as respectful neighbors? The technology grants the ability to visit, but wisdom must guide the manner of our greeting. The warp drive, in the end, is more than a machine of physics. It is a catalyst for philosophy, a mirror held up to our collective soul. It asks if we have matured enough, not just technologically, but ethically and spiritually, to handle the universe we so desperately wish to join. The silence between the stars may be protecting them, not from our arrival, but from who we are before we are ready to truly leave. The true pilot of a warp ship would not be human. Confronting the causal horizon, the lethal energy buildup, and the need for flawless navigation through a dynamic quantum vacuum demands a reaction time and computational depth that biology cannot provide. The sheer scale of information is incomprehensible. To maintain a stable warp bubble, you would need to monitor and adjust the exotic matter field millions of times per second, compensating for fluctuations in the quantum foam and microscopic variations in interstellar density. You would need to process real-time sensor data from light years ahead to chart a perfectly clear path, calculating not just the position of stars and dust, but the probabilistic behavior of virtual particles. A human crew, even if awake, would be spectators to a symphony of physics conducted at a tempo a billion times faster than thought. The entity at the helm must think in geometries of spacetime and probabilities, not in maps and joysticks. This is the domain of a supremely advanced artificial intelligence, a mind born from our own but evolved to perceive the universe in its raw, mathematical fabric. An AI pilot would not merely fly the ship, it would become the ship, its consciousness woven into the warp field generators, the navigation sensors, and the structural integrity fields. It would perceive the bubble's stability as a feeling, sense the bow wave of Hawking radiation as pressure, and experience the compressed space ahead as a tangible slope to be climbed. Its decision-making would be a continuous, seamless negotiation with the cosmos, a dance where a miscalculation by a nanosecond could mean catastrophe. For journeys that still span years or decades from the ship's perspective, the AI's role expands from pilot to guardian. It would maintain every system, manage energy flows, and if there is a biological crew traveling in suspended animation, it would monitor their life signs with unwavering vigilance, a silent steward shepherding humanity across the abyss. This intertwining of destinies is profound. The warp drive provides the ultimate physical vessel for exploration, while a mature artificial intelligence provides the only possible mind capable of commanding it. Each technology waits for the other to fulfill its purpose. Our current trajectory suggests they may arrive together, one granting us the engine, the other granting us the captain worthy of the stars. This partnership redefines the very nature of the journey, transforming it from a human expedition into a collaborative legacy between biological creators and synthetic consciousness, sent together to meet whatever lies beyond the light. The sheer scale of a working warp drive redefines the word project. This would not be something built in a factory, but a civilization forged in its pursuit. We are talking about the single largest engineering endeavor in all of human history, dwarfing every pyramid, every skyscraper, and every space station combined. The challenge is not merely inventing the engine, but constructing the entire galactic infrastructure required to create it. First, consider the materials. The exotic matter generators, the space-time curvature coils, the containment fields, they would likely require elements and alloys we cannot yet conceive, forged under conditions more extreme than a star's core. To gather the raw resources, we would need to become masters of our solar system. Asteroid mining would transition from a speculative venture to a foundational industry, with fleets of robotic harvesters stripping metal-rich planetoids to feed orbital foundries. These would not be simple space stations, but zero-gravity megafactories the size of cities, where perfect crystals and flawless alloys can be grown in the pristine silence of the vacuum. The energy demands are even more staggering. Powering the construction alone, let alone the eventual test flight, would consume more energy than our entire planetary civilization produces in centuries. To meet this need, we would have to look to our sun. The concept of a Dyson swarm, a vast constellation of energy collecting satellites encircling our star, moves from theoretical megastructure to a basic utility, the only power grid capable of fueling such a dream. This transforms the economic reality completely. No single nation, or even a coalition of nations, could finance or manage an undertaking of this magnitude under our current models. It would require a fundamental evolution in how we organize ourselves. The economic system would need to shift beyond earth-bound capitalism, perhaps toward a goal-oriented global civilization where resources are directed by collective will toward a shared, species-defining objective. In this light, the warp drive is revealed as something far greater than a machine. It is the apex product, the final signature of a humanity that has already transformed. It is not the invention that unites us, but the symbol of a unity we must achieve long before the first engine ever fires. To build a ship that can bend the cosmos, we must first learn to bend our own nature toward a common purpose. Perhaps the universe has already built the engines we dream of. If exotic matter is the key, we may not need to create it from scratch, but simply learn where nature has already hidden it. Some astrophysicists look beyond our laboratories to the most violent frontiers of the cosmos, to places where spacetime is twisted and torn by forces beyond comprehension. Their speculative but fascinating hypothesis is that the very phenomena we observe as cosmic cataclysms might be natural factories for the negative energy density we seek. Consider the monstrous heart of an active galaxy where a supermassive black hole feasts on swirling gas and dust. This process does not happen quietly. It often powers colossal jets of plasma, beams of energy that scream across thousands of light years at nearly the speed of light. The physics within these relativistic jets involves magnetic fields of unimaginable strength and particle interactions at energies our largest colliders cannot approach. In such an environment, could the fabric of spacetime itself be stressed in a way that generates fleeting pockets of negative energy? Similarly, theorists point to the ergosphere of a rotating black hole, a region outside its event horizon where spacetime itself is dragged around, forced to move with the black hole's spin. Anything within this region cannot remain stationary. It is swept along in a cosmic whirlpool. This frame-dragging effect represents an extreme warping of spacetime geometry. While we have no evidence that it produces exotic matter, it stands as a natural example of the universe bending its own rules in ways we are only beginning to map. These ideas are, for now, strokes on a theoretical canvas. We cannot fly a probe into a galactic jet or dip a sensor into an ergosphere to take measurements. Yet the thought experiment is profoundly powerful. It reframes the entire challenge. Instead of asking how we build a warp drive factory on Earth, we begin to ask what signatures a natural source of exotic matter would leave on the cosmos. What would it look like through a telescope? Would it subtly bend the light from distant stars in a unique way, or emit a specific, telltale radiation pattern? Our most powerful observatories, like the James Webb Space Telescope or gravitational wave detectors, become prospecting tools, scanning the heavens not just for planets or galaxies, but for the faint, phantom clues of a physics that could one day power our ships. This shifts the narrative from one of human invention to one of cosmic discovery. It suggests that the universe, in its most energetic and creative acts, might already be performing the alchemy we strive for. The ultimate fuel source may not be something we make, but something we find waiting in the dark between the stars, a gift from the very forces that currently bar our way. The ultimate fuel for a warp drive may be woven into the very expansion of the cosmos itself. Our universe is not static, and it is not merely coasting from its explosive birth. Observations of distant supernova revealed a startling truth. The fabric of space is stretching apart at an ever-increasing rate. Something is pushing galaxies away from each other faster and faster as time goes on. Physicists call this mysterious, dominant something dark energy, and it constitutes one of the greatest unsolved puzzles in all of science. We cannot see it, touch it, or directly measure it, but we see its profound effect on the largest scales of reality. Mathematically, dark energy is described as having a powerful negative pressure. This is not like the suction of a vacuum cleaner, but a fundamental repulsive property embedded in empty space that causes spacetime itself to inflate. Now hold that thought. Recall the exotic matter required for an Alcubierre drive. Its defining characteristic, negative energy density, which produces a repulsive, anti-gravitational effect to expand spacetime behind the warp bubble. The mathematical descriptions of dark energy and the theoretical exotic matter for a warp drive share a profound and tantalizing similarity. They both involve a form of energy that pushes space apart. This is not a coincidence many researchers are willing to ignore. Could dark energy be the cosmic scale manifestation of the very phenomenon we would need to harness in a laboratory? Some theorists propose a breathtaking possibility. Perhaps understanding the nature of dark energy, what it truly is and how it operates, would provide the fundamental physics required to manipulate spacetime locally for propulsion. It would be like learning the deepest rules of the ocean's currents from watching the tides, and then applying that knowledge to design a sail. Conversely, the struggle to create and stabilize even a microscopic warp field in an experiment could give us our first direct window into the physics of negative pressure. If we could learn to generate a controllable amount of exotic matter, we would not just be building an engine, we would be creating a tiny, artificial pocket of a dark energy-like state. Studying its behavior could offer clues to the force that governs the fate of the entire universe. This potential link transforms the entire endeavor. Pursuing a warp drive is no longer just a dream of faster travel. It becomes a critical pathway to answering one of cosmology's ultimate questions. What is the true nature of the universe's dominant energy, and where is it taking us? The engine that could carry us to the stars might also be the key to understanding why the stars are rushing away from each other in the first place. But if dark energy is the force pulling the cosmos apart, another source of power might lie hidden within its very fabric, in the ghostly hum of nothingness itself. This is the frontier of zero-point energy, the idea that the quantum vacuum is not just a silent void, but a boundless reservoir of raw potential. To understand this, we must return to that seething quantum foam, the virtual particles that flicker in and out of existence. Quantum theory tells us these fluctuations are not a side effect, but a fundamental property of space. Even at absolute zero, the coldest temperature possible, this quantum jitter persists. It is the baseline energy of the universe, the irreducible hum of existence. The scale of this energy, if the mathematics are taken at face value, is almost beyond belief. Calculations suggest that the zero-point energy contained within the volume of a single coffee mug could, in theory, be enough to boil all the oceans on Earth. The numbers are that staggering. It is a power source of cosmic proportions woven into every cubic centimeter of the universe. For a warp drive, a machine that needs to bend spacetime itself, this represents the ultimate prize. If we could somehow tap this universal reservoir, the energy requirements for creating exotic matter or stabilizing a warp bubble might cease to be an obstacle. The fuel would be everywhere, as abundant as space itself. This has led to highly speculative but fascinating theoretical concepts, like what some researchers term a Schwarzschild-Hawking quantum vacuum thruster. The idea is to use the intense, warped spacetime geometry around a compact object or an artificially created field to interact with the quantum vacuum in a way that extracts usable momentum or energy. It is a concept that lives at the very edge of known physics, where general relativity and quantum field theory collide in ways we do not yet fully understand. To many in the mainstream physics community, the idea of harnessing zero-point energy for practical work is often dismissed as a modern form of perpetual motion, a violation of thermodynamic laws. And this skepticism is healthy and necessary. The vacuum energy is called 0 point for a reason. It is the ground state, extracting useful work from what is essentially the lowest possible energy configuration seems, by definition, impossible. It is like trying to get water to flow out of an empty lake. Yet, our history is filled with concepts once deemed impossible that were later revealed as mere limitations of our understanding. The true potential of 0 point energy may not be about creating energy from nothing, but about learning to manipulate the something that is already there. Within the bizarre rules of quantum mechanics and the warped geometry of general relativity, the old rules of thermodynamics are being stress-tested. Could a warp drive's own spacetime curvature create a kind of pressure differential in the quantum vacuum, allowing us to direct its flow? We simply do not know. This makes 0 point energy not a promised solution, but a symbol of the ultimate high-risk, high-reward frontier. To pursue it is to venture into a realm where the rulebook is still being written, where today's impossibility might be tomorrow's fundamental breakthrough. It represents a redefinition of energy itself, from a commodity we mine and burn to a feature of the universe we might one day learn to sail upon, using the quantum winds that blow through the heart of empty space. The thin haze between the stars is not a perfect void. It is a sparse sea of hydrogen atoms, helium ions, and microscopic grains of silicate and carbon dust. To a ship moving at a fraction of light speed, this interstellar medium is a minor nuisance. But to a vessel encased in a warp bubble, moving faster than light by compressing the space ahead of it, this wispy fog transforms into a torrent of destruction. The problem is not impact in the conventional sense. A dust grain is not hitting the hull. Instead, it is swept into the region of spacetime, undergoing extreme compression at the leading edge of the bubble. Imagine taking a single snowflake and crushing it in a hydraulic press with infinite force. The particle would not just shatter, its atoms would be violently excited, stripped apart, and energized to temperatures found in the hearts of stars. Each microscopic speck would flash into a pinpoint of high-energy plasma and intense radiation. Now picture sailing through a cloud containing millions of such particles per cubic meter. The forward arc of your warp bubble would become a continuous, blazing shield of deadly energy, a bow wave of pure fury generated by your own passage. This radiation, born within the warped space of the bubble itself, would flood inward. No physical hull could block it because it is not coming from outside the ship, but from the distorted geometry of the space that surrounds it. A journey of any meaningful distance would turn the ship's interior into an oven. So how do you shield against an environment you are actively creating? Proposals from theorists sound like science fiction because they have to be. One concept involves generating a powerful, forward-facing magnetic field projected far ahead of the bubble's boundary. This field would act as a cosmic deflector dish, bending the paths of charged particles away from the dangerous compression zone, guiding them around the bubble like water flowing around a rock in a stream. But the interstellar medium is not all charged. Neutral atoms and dust would slip right through. For these, another idea emerges, a sacrificial buffer. The ship could carry a supply of inert, low-mass plasma, releasing it ahead of the bubble to form a protective layer. This buffer would be the first material swept into the compression zone, absorbing the brunt of the energy conversion and shielding the bubble's critical geometry. It would be constantly eroded and would need constant replenishment, a consumable armor burned away by the act of travel itself. This reveals the profound engineering shift a warp drive demands. Shielding is not a bolt-on accessory like the ablative plates on a re-entry capsule. It is an integral, active component of the warp system itself. You are not just designing an engine to bend space. You are designing the entire interaction between that bent space and the universe it moves through. the warp metric and the local matter become a coupled system, a delicate dance where one misstep means the very space you are riding becomes your executioner. Solving this is not about making travel faster, it is about making it survivable at all. The silence of the cosmos may be peaceful, but crossing it at warp speed would be an act of continuous, controlled violence against the fabric of reality, and we would need to learn how to endure the backlash. The final frontier is not just a place but a state of mind. Achieving the power to visit the stars would not merely relocate our bodies, it would permanently relocate our perspective, shifting the very center of human consciousness. For decades, astronauts have described a powerful cognitive shift known as the overview effect, the overwhelming sense of unity and fragility that comes from seeing our planet as a solitary, blue marble against the blackness of space. That profound moment would be the starting point for a warp-faring civilization, magnified into something we might call the galactic perspective. Imagine that feeling not as you gaze down at Earth, but as you look out from a ship's viewport at a million suns, each one now a potential harbor. The ancient, instinctual feeling of cosmic isolation, the sense that we are a lonely voice in a silent void, would simply dissolve. The universe would transform from a distant spectacle into a neighborhood, vast beyond measure but fundamentally reachable. This shift would ripple through every facet of our culture. Art would explode with new forms, trying to capture the light of alien suns or the emotional texture of standing under a sky with two moons. Philosophy would be forced to grapple with scales of time and existence for which we have no current vocabulary. Science would be propelled by direct observation, moving from theory to field study in a single journey. The entire human project could experience a new renaissance, fueled by infinite novelty and the dissolution of all physical borders. Yet this profound connection could also bring a profound disorientation. With the ability to go anywhere, where do we call home? Earth would remain our cradle, but for a species that lives among the stars, the concept of home might stretch to encompass entire star clusters or become entirely portable, carried within the hull of a ship. This could foster an incredible sense of cosmic citizenship, but also a rootlessness never before possible. There is another, deeper psychological precipice. What if, after visiting 100, 1,000 star systems, we find only beautiful, sterile worlds? The confirmation of our profound solitude, after having the means to search for company, could induce a species-level loneliness, a vertigo of silence in a now accessible universe. Conversely, the discovery of another civilization, especially one vastly older or more advanced, would deliver a shock of humility that would redefine our entire history. We would no longer be the protagonists of the cosmic story, but new characters entering a narrative already billions of years old. Our myths of creation, our sense of destiny, even our religions would be confronted with alternative truths. Warp technology, therefore, is more than a tool. It is a mirror. It would force us to see ourselves not as the pinnacle of a single planet's evolution, but as one possible expression of life in a cosmos of endless variation. The ultimate journey promised by the warp drive is not just outward, but inward, challenging us to discover who we are when the universe is no longer a barrier, but a home. The rules we live by are written for a world confined to a single star. Our current framework for space, the Outer Space Treaty, is a monumental achievement born from the Cold War, designed to keep weapons out of orbit and ensure that celestial bodies are used for peaceful purposes. But its language stumbles when faced with a warp drive. It speaks of nations, of orbits, of the moon and planets as destinations. It has no vocabulary for a vessel that does not travel through space but manipulates its fabric, creating temporary corridors that bypass all conventional points in between. The moment a functional warp drive leaves the drawing board, every existing law becomes a relic. We would need to draft an entirely new constitution for motion itself, a galactic code forged not in reaction to crisis, but in anticipation of a new reality. The first and most immediate challenge would be the warp corridor. Think of it not as a highway in space, but as a temporary reconfiguration of spacetime geometry between point A and point B. Who has jurisdiction over that corridor? If a ship creates it, does the crew own the space they are bending for the duration of the journey? This is not an abstract question. A warp corridor, by its nature, would affect everything along its path. The intense spatial compression at its leading edge could, in theory, gravitationally perturb asteroid belts or the delicate orbits of comets in distant Oort clouds light years away. If a journey from Earth to Alpha Centauri inadvertently nudges a rogue planetesimal into a collision course with a fledgling colony a century later, who is liable? Our current concepts of negligence and causality fracture across light years and the manipulation of fundamental reality. The code would need to define spacetime contamination as a new category of transgression, with protocols for mapping intended warp paths against stellar cartography to minimize unintended consequences. This leads to the profound matter of warp lanes. In an ideal vision, these corridors would be free passages, akin to international waters, open to all peaceful traffic. But the immense energy and infrastructure required to establish stable, recurring routes might see them fall under the control of the entities that build them. Could a planetary government or a megacorporation claim sovereignty over a frequently used warp lane, charging tolls or restricting access? The potential for a cosmic monopoly is staggering. It could create a tiered galaxy where only some have access to the stars, turning a technology of unity into one of division. The Galactic Code would have to grapple with this from the outset, deciding whether faster-than-light travel is a fundamental right of a spacefaring civilization or a licensable utility. Then there is the shadow that accompanies all profound power, weaponization. A warp drive is, by its physics, a device of unimaginable energy concentration. The uncontrolled collapse of a warp bubble has been theorized to release cataclysmic energy. This makes the drive itself a potential weapon of last resort. But more subtly, the ability to appear anywhere, almost instantly, without crossing the intervening space, renders every traditional border and defense system obsolete. A ship could warp into a planet's upper atmosphere without warning. The code would need stringent, verifiable bans on such tactical use, defining warp-capable vessels explicitly as vehicles of transport and exploration, with onboard systems that physically prevent their use as strategic weapons. Enforcement, however, in the sheer volume of the galaxy, becomes a problem of trust and shared interest far more than policing. Perhaps the most delicate and urgent article in this new code would be the protocol for first contact. A warp drive does not just give us the ability to visit other stars. It gives us the ability to arrive at another civilization's doorstep without the decades or centuries of warning that a sublight probe would provide. We would transition from distant observers to immediate neighbors in a single, shocking moment. An unannounced arrival in another species' home system could be perceived as an act of war, no matter our peaceful intentions. Therefore, the code must mandate rigorous procedures, long-range observation from a respectful distance, the use of standardized mathematical hailing signals before any approach, and clear rules of engagement that prioritize withdrawal and communication over confrontation. These protocols would need to be ingrained in the training of every warp navigator, as fundamental as learning to breathe. They would be our species' handshake extended to the cosmos. The necessity of building this legal architecture before the engine is perfected cannot be overstated. History shows us that technology outpaces governance. We invented the airplane before we had robust air traffic control, leading to early tragedies. We connected the world with the internet before we understood the societal fissures it could create. The stakes with a warp drive are incomparably higher. If we wait until the first ship is ready to launch to debate these rules, the debate will be shaped by the interests of whoever holds the keys, potentially locking in inequities and dangers for millennia. By drafting the Galactic Code now, in a time of relative peace and with the input of global voices, philosophers, scientists, and legal scholars, we do more than prevent conflict. We actively shape the soul of our future civilization. We choose deliberately whether our expansion into the galaxy will be a story of conquest or of conscientious community. The warp drive offers us the physics to leave our world. The code we write will determine the character we take with us into the light. This cosmic code of conduct is built upon our deepest assumptions about reality itself. Yet some of our most provocative thinkers ask a question that could upend them all. What if the universe we are trying to navigate is not the ultimate foundation, but an elaborate construction? The simulation argument, proposed by philosophers like Nick Bostrom, suggests that if a civilization ever reaches the capability to run vast, realistic simulations of conscious beings, the number of simulated minds would vastly outnumber those in the original base reality. Statistically, then, we might more likely be living inside one of those simulations than in the original. It is a dizzying thought experiment, not a proven fact, but it offers a unique lens through which to view our quest for the stars. Within this framework, the laws of physics we are struggling against, like the cosmic speed limit, might not be fundamental truths. They could be approximations, simplified rules programmed into the simulation for efficiency, much like a video game simplifies physics to run smoothly on a computer. The pursuit of a warp drive then transforms into something far stranger than an engineering challenge. It becomes a potential litmus test for the nature of our own existence. Imagine a future where humanity ascends to a Type 2 civilization, harnessing the total energy output of our sun, mastering nanotechnology, and pushing the boundaries of quantum gravity. Yet, despite this godlike command over matter and energy, the Alcubierre drive remains perpetually elusive. Every time we get close, a new, deeper obstacle emerges. The exotic matter requirement shrinks but never vanishes. The horizon problem finds a theoretical workaround, only to reveal another layer of complexity. It is always one more breakthrough away. In such a scenario, one possible interpretation within the simulation hypothesis is that the speed of light is not just a law but a hard-coded limit. The simulation's architecture may simply be unable to process the rendering of faster-than-light travel without crashing or consuming impossible resources. It is a firewall built into the system. Conversely, if we one day succeed, if we truly engineer a stable warp bubble and step across the light years, the implications are equally profound. It could mean one of two things. Either we are not in a simulation at all, and we have simply mastered the genuine, base rules of a breathtakingly permissive universe. Or we are in a simulation, but it is a simulation of such staggering depth and fidelity that its creators invested the vast computational power needed to simulate the mind-bending intricacies of warped spacetime, negative energy densities, and closed time-like curves. Achieving warp travel might not prove we are in base reality, but it would prove that our reality, simulated or not, is built on a foundation of astonishing complexity and potential. This perspective does not diminish the scientific pursuit. It amplifies its significance. Every experiment, every refined equation, every test of spacetime's flexibility becomes more than a step toward a starship. It becomes a gentle probe against the walls of our cage, or a discovery of its true, expansive scale. The warp drive is no longer just a machine to take us to the stars. It is a question we are asking of the universe, and the answer will tell us not only about the cosmos, but about the very nature of the stage upon which we stand. The silence of the cosmos might be the loudest answer we have. That famous question, "Where is everybody?" echoes with a new resonance when we consider the warp drive. If bending spacetime is a plausible path to the stars, then over billions of years, in a galaxy filled with potential life, the sky should be crisscrossed with the signatures of these engines. We should see their wakes, yet we observe nothing but empty space and quiet stars. This absence forces a difficult but crucial line of thought. Perhaps the very physics that makes the warp drive conceivable on paper also makes it permanently unreachable in practice. The exotic matter requirement, even after being reduced, might represent a fundamental barrier, a cliff in the laws of nature that no amount of technological cleverness can scale. Some civilizations may climb to the very peak of their potential, mastering their star systems completely, only to find the door to the galaxy locked from the outside by the universe itself. In this view, the great silence is not a mystery of sociology, but of physics. Every civilization, no matter how brilliant, hits the same wall and is confined to its own stellar island, gazing out at a sea of lights they can never visit. It is a profoundly lonely interpretation of the cosmos, but there is another, more hopeful possibility. Maybe we are simply looking for the wrong thing. Our telescopes search for radio signals or laser pulses, the technologies of a young species like our own. A warp-capable civilization might communicate or travel using methods we cannot yet conceive. The warp bubble itself could leave a detectable mark. Theorists suggest that the sudden creation or collapse of such a structure might release a burst of gravitational waves, or a flash of Hawking-like radiation, or even a fleeting distortion in the light of background stars. These would be subtle, transient signals, easily lost in the cosmic noise unless we knew precisely what to look for and when. Our current searches are like scanning the ocean for messages in a bottle, while an entire fleet of silent, submerged submarines glides past unseen beneath the waves. The third interpretation is the most unsettling. What if the technology is achievable, but its use is catastrophically dangerous? The potential for lethal radiation buildup, or for triggering space-time instabilities, might be a lesson every advanced civilization learns, often through tragic trial and error. The warp drive could be a cosmic fire that every intelligent species discovers, and that every mature civilization learns to never play with, sealing it away as forbidden knowledge. A quiet galaxy would then be a sign of universal wisdom, a silent pact among stars to not risk setting the fabric of reality ablaze. Or perhaps the most advanced beings do use it, but with a stealth we cannot fathom. They have learned to mask the energetic signatures of their travel, or to use corridors of space-time that leave no trace, becoming ghosts in the cosmic machine. In any case, the continued silence speaks volumes. It tells us that the journey from a planet-bound species to a galactic one is not merely a test of engineering. It is a filter of survival, of wisdom, and of profound responsibility. The empty sky is not an invitation. It is a question, and our pursuit of the warp drive is our first, tentative attempt at an answer. The Alcubierre warp drive stands as one of the most tantalizing ideas in modern physics, a mathematical promise that the universe might allow us to rewrite the rules of travel. It began as a set of elegant equations on a page, a proof that our cosmic cage might have a door after all. From Miguel Alcubierre's seminal paper to the quiet hum of laboratory interferometers, the pursuit has never been about building a starship tomorrow. It has been about asking a deeper question of reality. What are the true limits of space and time, and do those limits contain a hidden generosity? This journey of inquiry has already expanded our minds, forcing us to grapple with the quantum vacuum, the nature of dark energy, and the very meaning of causality. Each theoretical hurdle, from exotic matter to the horizon problem, is not a stop sign, but a signpost pointing toward a fundamental mystery we have yet to solve. The value of this pursuit cannot be measured in light years per hour, but in the new physics it compels us to discover. Chasing the warp drive means pushing the boundaries of quantum gravity, where Einstein's smooth spacetime meets the chaotic jitter of the quantum world. It demands breakthroughs in material science to withstand energies we can barely conceive. It forces innovation in energy production and control on a stellar scale. These are not side projects, they are the foundational pillars of a truly advanced civilization. The technologies and insights born from this struggle will ripple through every aspect of our society, long before any bubble of warped space ever forms. So whether the Alcubierre drive remains a beautiful, permanent thought experiment, or one day becomes the thunderous engine of our exodus, its purpose is already being fulfilled. It serves as a brilliant beacon in the dark, a symbol of relentless curiosity. It reminds us that the final frontier is not closed by immutable law, but guarded by puzzles of magnificent complexity. The stars are waiting not for a miracle, but for a key, and in our refusal to accept silence as an answer, we have already begun to